Welcome, everyone. Well, let's get started. So we're actually going to start with the big one, our main integration rule, and that's substitution rule. And hopefully you saw this in Calc 1, so this is kind of review, but we use it so much where it's definitely worth reviewing here. And some of our other integration techniques actually rely on this a bit. So we're going to look at substitution rule just for indefinite integrals, and then we'll see later on how to do it for definite integrals. So not much extra there. And there is a formula for substitution rule. And we'll come back and look at this in a little bit. See what's going on. You almost don't want to, it's not even really worth remembering the formula here. We actually just want to think of substitution rule as more of a process. So we'll come back and look at what this rule actually says. I think we'll start with an example. So kind of a tip for when we'd actually use substitution rule is if the function we're considering is not one of our basic integrals. So this isn't just a basic power function. There is a power function, so this is raised to the power 10, but then we have all this other stuff going on inside the parentheses. So the tip here is if you see parentheses, well, you're most likely going to have to use, and you see a bunch of things inside those parentheses, substitution rule might be in your future. So let's actually see in this example how substitution rule works, and then we'll go back to the formula. So the function here is 3x plus 4 raised to the power 10 times 3. So there's our function. And the first step with substitution rule is we want to choose, let me use a different color. We want to choose a value for u. So a lot of times you'll hear this called, and I'll probably call it u substitution. So we're going to usually, the first step here is pick what u is. And when we do this, we normally let u equal what's inside the parentheses. So in this case, 3x plus 4. So we're going to let u equal that 3x plus 4. Okay. Well, the next kind of piece of this is we're going to calculate something that we call the differential. So we're going to calculate du. So this is the differential of u, du. And the way we calculate this is we just do the derivative of the function here. So just do a regular derivative, and then we multiply by dx. So in this case, the derivative of 3x plus 4, derivative of 3x is 3, and then the derivative of the plus 4 is 0. So our derivative here is just 3. And for the differential, we're just going to multiply by dx. All right, so that's the first step. First step is to choose u and calculate du. And normally choosing u, that's kind of the hardest thing with these. Because it's not always obvious. But the kind of the sign here is you want to look for parentheses, and then you want to look for a bunch of things inside those parentheses. All right. So the next step is we actually want to produce, basically we want to plug everything in. We want to substitute everything in. So we want to substitute these values. We want to plug in our choice for u and what we calculated for du. So let's look at how this is going to work. All right, so this 3x plus 4. Well, instead of 3x plus 4, let's change that to a u. So we're going to have u. You can still write the parentheses if you want. And then this is raised to the power 10. Okay. So that was our u. Now what about this 3, use a different color. What about this 3dx here at the end? Well, if we look down, we have a 3 times dx down here, and that's what we calculated for this new differential, which we're calling du. So we're going to fill that in. So we're going to change that 3dx, we're going to change that to our new differential du. All right, so this gives us a nice simplified integral to do. So we've gone from having an x integral, which there was a lot more going on here, to now just this simplified u integral. And so all the x's are gone. Now we only have u's here. And now this integral is actually something that we can just do. It's one of our basic integrals. So that's the next step. Step 3 is to actually just calculate this u integral. So what do we get? Well, we have this power function u raised to the power 10, so let's break out our power rule. So we keep the variable the same. We add 1 to the exponent. We take that new exponent that we got, flip it, put it in front, so we have 1 over 11 times u raised to the power 11. And then we're doing an indefinite integral, so we throw on a plus c at the end. So there's our step 3. And then the last thing we got to do is we just got to convert this back to x. So we're almost there. We have the antiderivative, but the original function we were integrating here had all x's in it. So we don't want u. It's just kind of a temporary variable that we introduced. We want to get back to x. So right here, instead of having u, let's kind of write out the setup here. We're going to fill back in. So we have the 1 over 11. We have the 1 over 11. We have the raised to the power 11. So the power function, that part stays the same. Still have our plus c there at the end. But now instead of this u, we're going to actually fill back in for what u actually was equal to. In this case, the 3x plus 4. So let's throw it in there. And there we go. We have our antiderivative. So this is how substitution rule works. You want to think of this almost as a process. So the 3x plus 4 here was inside the parentheses, and that was how we chose u. So if we go back up, again, there is a formula for substitution rule. And the way we choose u is we're choosing u to be the inner function. So when we have this whole big complicated mess of a function that we're trying to find the antiderivative of. Look at this thing. It's complicated. And we look for the parentheses and we pick what's inside those parentheses. So that's our u there. So normally we're going to let u equal the inner function. So first step, choose u. And then the next step is we calculate the differential du. And the way we calculate this, again, is we calculate the derivative of our whatever choice we made for u. So in this case, we chose u to be g, so we're going to calculate du to be g prime, and then we throw on a dx. We multiply it with a dx at the end. And that's what we're seeing right here. So when we make our substitution, we have this inner piece, this inner function, the g, how we chose u, that becomes our u term. And then all of the leftover terms kind of usually get swallowed up into our differential. We'll see that it's not always so nice. It's not always a perfect match like this, where you have all this other stuff and it matches up perfectly. Sometimes we have to do a little bit of extra work there. So sometimes this differential part, we gotta take it easy. The The outer part of our function, though, just stays the same. So that's the part that's kind of hopefully easier to integrate. And that's what we saw in our first example here. So the inner part became our u. The leftover part here became our differential du. And we kind of this one's nice. This is a nice first example because this is a perfect match. Again, that doesn't always happen. But the outer part of our function, this raised to the power 10, that actually still, that's the thing that we actually integrated. And so one little warning about doing the substitution rule here is that in order for us to kind of go through with the integration, in that step 2, we have to get rid of all the x's. So we have to convert all the x's that we see into u terms. So that's what we have. In the original integral, there's an x here, and then there's an x in that dx there. When we went into step 2, only u's. So if I had left this as dx, we'd have to do something about it. So I have to get all u terms over here. All right, so how do we actually choose u? Well, we want to identify what the inner function is, so you want to look inside the parentheses, and then it comes down to the outer function, what's going on the outside. So, if we have a power function, you see parentheses and then something complicated getting raised to some power n, well, you're going to choose u to be what's inside the parentheses. If we have an exponential function, and that's the complicated piece, and there's a whole bunch of stuff up in the exponent there, well, you're going to let u equal the terms that are in the exponent. And if we have a fraction, where it's 1 over just some terms in the denominator, well, you're going to let u equal those terms in the denominator. And it all comes down to these kind of basic antiderivatives that we've seen. When we have u raised to the power n, we get to use power rule. When we have 1 over u, we get to use this natural log 1. And if it's e to the u, well, then it's all nice. And there's similar things for like trig functions as well. So if you have say sine so we might also see this with trig functions. So if I had like sine of a whole bunch of stuff inside the parentheses, well, then I'd let u equal the stuff that's inside the trig function. So this kind of gives us a starting point for what we can do. And let's just look at example 2. We're not going to finish this one. We'll finish this one in class. We have this function 2x times e to the x squared. And when I look at this, again, when we write an integral, this integral sign just means find the antiderivative. And the dx here at the end just means, well, what variable are we integrating with respect to? So we're really kind of focusing in on this function that's in between those two things. So we're focusing in on this function. And you want to kind of look for the more complicated part of this function, more complicated piece. So when I look at this thing, we have this like 2x piece, and then we also have this e to the x squared piece. And compare these. Which one do you think is more complicated? So, 2x, there's a little bit going on there. Got some multiplication. But definitely there's more going on with this e to the x squared piece. So I would consider that to be the more complicated piece. And so we have this situation where we have an exponential, e raised to, and there's more than just an x up there. It's an x squared. So there's a bunch of stuff going on up in the exponent there. So we're in this situation where we have e raised to a bunch of terms. So we're going to let u equal those terms that are inside the exponent. So again, first step here is to choose u and calculate du. And our choice for u in this case is going to be that stuff in the exponent, x squared. And so when we calculate du, the differential du, how do we do that? Well, we differentiate the x squared function, so we get 2x, and then we multiply that by dx. So again, this is the differential. So when we calculate this differential, we're going off of what we chose for u. So, forget about the integral here for just a second. Once we choose u, then your hand is forced. You have to calculate du by doing the derivative and then multiplying by dx. So in this case, the next step then is to kind of start to substitute in the values here. And if you can, give this one a try, but we're going to finish this up in class. So we'll see you then. Bye-bye.